Hey everybody, this is Bob with EdWorks. This video is going to be rather detail oriented about converting a light machine's control box into a format that we can utilize using some standardized components. It's not for everybody. The audio isn't all that good. It's just for those people that actually want to do this project. It allows you to follow along and complete it. So heads up. Let's take a minute to talk about converting the light machine's control box to something that we can use. Light Machines makes this control box. I've done 3 conversions now. All 3 boxes have been different. I don't even want to suggest that these are the same because these machines were made for many years and these boxes changed with the times. And this is one of the earlier models, I believe. And so we're going to just take this thing and remove all their proprietary components and put in standardized components. So this is what it looks like when we open it up. You can see the circuit board, the power supply, some heat sinks. And when we're done, we want it to look something like this. So before we get going, let's just talk about what's going on in here. On this circuit board on the right side, that's your logic that receives input from the computer and converts it into signals that can control steppers. There's a power conditioner. There's 3 large capacitors and 2 large capacitors and 2 large resistors. This is what conditions the power, and we'll talk about that later. There's a giant heat sink. There's 4 chips that control stepper motors. They produce a lot of heat, and they need a heat sink. On the back side, we have a fan that draws air in and out the sides. There's fuses for the different components, and there's power out and power in. There's 3 power outlets. There's 1 power inlet. Below the power outs is the transformer, which I got marked with a big T. On the front of the box, there's some switches. So, this is where we're headed, and this is where we started from. First order of business is we're going to pull that board out and remove it. Next order of business is I need to cut an aluminum plate. This plate is 1/8 of an inch thick. It's the same size as the circuit board. What I did is I put the circuit board on top of the plate. I drilled out 1 corner hole. When that hole was complete, I put a screw through it, and then I went to the opposite end of the board diagonally and screwed a second hole and put a screw in that. Now that the circuit board was affixed to the aluminum plate, I was able to drill out the other 6 holes. There's 8 total. Once I got that done, I was able to put the plate in the box and screw it down. That worked out quite well. Now I have a surface that I can mount things to. So the first order of business is to mount steppers. I have 4 very standard steppers. You've probably seen these. They attach on the right and left side. There's a tab. So what I do is I put them on the plate. I drill some holes and I put some self-tapping screws in there and mount them to the surface. They're mounted. With that, I take a Sharpie pen and I label them X, Y, Z, and A. Next up is the power conditioner. I take the 2 big capacitors off the circuit board and the resistor. You can see the 2 capacitors, the resistors on the right, and I make a board, and I'll show you the circuit for that, that will condition the power. This is very helpful. Next, I get that mounted in the machine next to the steppers, and I try to determine what kind of voltage my transformer puts out. I hook up to 1 wire and I'm getting 22.7 volts. That's probably the 24 volt line. I hook up to another wire and I get 46.8 volts, and that's the 48 volt line. My goal is to use the DB connectors on the back of the board. These DB connectors do not have room when the aluminum plate is in there to be used, so I had to cut the plate in half to make room for my DB connectors. DB connectors can be bought with a breakout board connected to them. So once they're installed, you have a breakout board on the backside to attach your terminals and attach your wiring. So what I did is I bought 4 DB connectors, and we attached all the wiring to these breakout boards, and it worked quite nicely. Unfortunately, my aluminum plate was in the way, and so I had to cut it in half to make room for these DB connectors. So what I have here now is I've labeled my 24 volt wire and I've labeled my 48 volt wire. Let's look at the schematic and see what we're talking about. On this schematic we have AC in, and we go to a diode called a bridge diode, and what that does is it sends the alternating current into a pattern that's all DC current. So rather than an alternating sine wave of positive and negative voltage, the negative voltage gets clipped into positive voltage, and you end up having a DC out that looks like a very sawtooth pattern. To that output, we attach two capacitors in parallel and one resistor, again in parallel. So the two capacitors will condition that voltage so it no longer looks like a sawtooth and more looks like a constant voltage. These capacitors are quite simply just put in parallel with a 5K 3 watt resistor, and I had those all from the board, so I didn't need to buy anything. The power requirement for the 5K resistor is probably about a half of a watt, and so we got plenty of reserve with a 3 watt resistor. This is what the waveform looks like without a capacitor. It's a sawtooth wave. When we add the capacitors, it smooths out that sawtooth. The capacitors will hold the charge, and we lose those little valleys, and the peaks seem to stay in place, and we end up with this pattern here. So now the voltage, rather than going from 0 to 24 or 0 to 48 as we move along in time, it stays up at probably the 22 to 24 volt range, and probably the 46 to 48 volt range. So this is a unregulated linear power supply. Next up is the DB connectors. I have two DB9 connectors and a DB25, and here you can see how they extend into the box, and unfortunately they didn't go above the aluminum plate. They actually interfered with the aluminum plate, so the aluminum plate was removed. So I have a DB9, a DB15, a DB9, and a DB25. The DB25 connects to the computer. The DB15 handles the X and the Y axis, as well as their associated microswitches. The DB9 handles the Z-axis with its two microswitches. The other DB9 between the DB15 and DB25, that's going to end up being for the fourth axis, also known as the A-axis. So now here we kind of have it. We have our stepper drivers that are installed. With the stepper drivers, we got our power conditioner, which is installed. This is what it looks like before we started. This is what it looks like after we were done. With the cover back on, we end up with a box that looks identical to where we started. This box has no more holes drilled in it. We're utilizing all the connectors that were in it. So basically, we took this box, we converted it to standardized components, nothing proprietary, everything we can deal with, and now we just have to tackle the wiring.
Well, I hope you found this video helpful. It's a very detailed video on how we put standardized components in this Light Machines box. Certainly not for everybody, but if you're going to do one of these projects, you might find the information enclosed in this video to be quite helpful. Have a good day.